Good day everyone. I am Demosthenes Dingkong. So today we are going to report about principles of watertight integrity. So in the end of the discussion, we expect you to explain the basic principles of watertight integrity and calculate transverse stability after a compartment has been damaged. So, background information, watertight integrity is defined as closures or fittings that prevent the ingress of water to certain compartments. So, this original watertight integrity may be reduced or destroyed through enemy action, storm damage, collision, stranding, or negligence. So, another damage stability of a surface ship comes use when the ship's watertight hull affected in a way that allows water to flood any compartment within the ship's hull within the ship's hull. So in addition, this approach uses concept of probability to ensure that ships can survive damage to its compartment. So there are probabilities factors that are used in approach. Probability that a particular compartment will damage in an accident. So do you remember that scene from the movie Titanic where after the ship hit the iceberg, the naval architect lays down the ship's plans in front of the captain? So while he was trying to brief the captain about the situation, so the captain just had this one question: how much do we have? How much time do we have? So and he said an hour, two at the most. So how did he arrive at this number, and how was he sure that an unsinkable ship is going to sink? So the members of the group will discuss further about this situation. But that is what damage stability is all about. So all the rules about damage stability are trying to keep the ships safe even after one or more compartments are breached. So that's all my part. Thank you.
Consider this. You have two ships both identical in every respected, but the first one has only one tank or cargo hold, and the second one has two tanks or cargo holds. Which one do you think is safer? Easy answer, right? The one with the two cargo tanks. This is because if one component is flooded, the first ship will have 100% of the cargo space flooded. The second ship would still have 50% of the cargo space intact. What I am trying to prove here is that more the subdivisions of the ship, safer it would be. But the ship owner cannot divide the cargo space in 20 or 50 compartments. This would mean the use of more steel, more money to build the ship, and lesser the cargo space to use. Ship owner cannot build a ship with just one compartment either. That is too unsafe. So, how many minimum subdivision a ship must have? All in all, there are three approaches to building a ship that can withstand damage to its compartments. All the three approaches for damage stability are just aiming to find the answers. So let us discuss each of these approach of damage stability. Number 1. Floodable length and factors of subdivision. This is an old approach, but it is still important to discuss this because this approach lays the foundation to understand the damage stability. In this approach, the number of subdivisions required is calculated by knowing the floodable length along the ship. Floodable length is the length of the compartment which is flooded will cause the ship to sink up the margin line. Let us understand this by building a ship. We have a ship and we need to put subdivisions or bulkheads to it to divide the ship into compartments. We create one compartment in the midship by placing two bulkheads. Let us mark this bulkhead as A and B.
The length of this compartment link EB need to such that if this compartment is flooded, the ship will sink to a point where margin line is just submerged. This is the floatable length of this point. Now we want to place another bulkhead aft of midship. Again, this bulkhead needs to be at a location such that if compartment EC is flooded, the ship will sink to a point where margin line is just submerged. And with this same approach, we can decide the location of other bulkheads along the ship length. When calculating the floatable length, one thing that we need to keep in mind is that we need to float the compartment to the full width of the ship, even when we have or plan to have a certain line bulkhead. Floatable length curve. Our ship is ready now with all the compartments it needs. This ship would not sink if any one compartment is breached and flooded. But if you would have noticed, I have drawn larger compartment in the midship area. This means that I have shown large floatable length closer to the midship area. This is because if the midship compartment is flooded, the ship will sink bodily with least trim.
The damage stability rules of the ship would be something like the ship should be able to survive the branch of any one compartment. To check if this ship comply with these damage stability requirements, the floatable length curve is superimposed on the ship's plan. But as we move away from the midship, the floatable compartment will trip the descent. This would make a smaller compartment to sink the ship up the margin line. So, the bottom of the line is that the floatable length changes along the length of the ship. Floatable length curves represent the maximum floatable length of the ship along the ship's length. This curve is obtained by vertically plotting the floatable length along the ship's length. Checking the damage stability compliance. Floatable curve method. So far, I have given the basic idea of what floatable length and how floatable length curve is obtained. Ships that require to comply with this method of the damage stability would be provided with the floatable length curves.
On the damage stability compliance is checked. The length of the assumed damage compartment is plotted vertically at the center of the compartment. In this length below of the floatable length curve, this compartment complies with the damage stability requirements of the compartment standard. Check the picture below. Same is done with other compartments. As we can see, all the length triangle are with flyable length curve of the ship. This means that this complies with one compartment standard of the damage stability. Now, let us check the damage stability compliance for two compartment standard. In this case, we will assume that flooding of two compartments and compare the length triangle with the floodable curve of the ship.
We can go in a similar way if we want to build a 3-compartment or 4-compartment ship. So remember, Titanic was a 4-compartment ship and so was called the unsinkable ship. So let's talk about a compartment. A compartment is a portion of the space within the ship defined vertically between decks and horizontally between bulkheads. It is analogous to a room within a building and may provide watertight subdivision of the ship's hull, important in retaining buoyancy. If the hull is damaged, subdivisions of the ship's hull into watertight compartment is called compartmentation. So again, same is done assuming floodings of any two adjacent compartments. Clearly, this ship does not comply with damage stability requirements of two compartment standards. if we need to comply with 2 compartment standards, this ship needs to have more compartments. So kani siya nga barko, kuwangan ni siya sa 2 compartment standard. So need jud siya mapunan og compartments like 3 compartments or 4 compartments para maglisod siya, dili siya maanod ba, dili ma-damage like. So the length of which need to be such that even when 2 compartments are flooded, it will be below the floodable length curve. Maybe the below subdivision of the ship will be able to satisfy the damage stability requirement for 2 compartment standards. So let us check the damage stability compliance to the 2 compartment standards. So as you can see, this ship is a 2 compartment standard ship now.